Okay. First thing, no update on the flame test lab. Still hasn't been fixed. Hoping to get some more information today or tomorrow. Hopefully we can get it done this week, but I'll let you know as soon as I know anything more. All right, then our focus starting in this week is strictly quantum mechanical model. We're going to learn a lot today about how exactly the quantum mechanical model views the structure of electrons within an atom, and then that leads us into trying to describe that. That's a big part of this unit is can we actually describe the electronic structure within the atom. So having said that, we don't really have homework coming up till Wednesday. We got 2.5 to 3 days of like good solid notes that might be a little much. So just sharing some study tips like I tend to do. One thing, in case you weren't familiar with this, rereading notes daily, almost daily, just kind of going back through, looking over them again, not just waiting until the night before the test. That can be helpful. In addition to possibly rewriting, there is plenty of studies about the connection between you physically writing things down and that being retained in your head, right? That information. There are lots of studies with that. Even I know with flashcards, they talk about you write out your flashcards versus having like a Quizlet that already has them for you. It's just a different connection. They talked about it with lecture notes, typing notes versus writing notes. So there is a big connection there. So something that I encourage, because in this unit, there's not quite as much to do, and there's more to know. That sometimes can be challenging for students, and it can make it a more challenging test. So I think going back over the lesson worksheets that we've been doing, the notes that we're going to start taking, that can kind of help whenever it comes to your test next Tuesday. Okay. So here we go. With that, quantum mechanical model. All right, so if you recall quantum mechanical model, let's just remember good things from Bohr's model. We still have quantized electrons. We're still going to talk about energy levels. Okay? However, these energy levels are absolutely not circles. They are going to be all sorts of crazy three-dimensional structures. Okay? But we still like this idea of electrons being quantized and being confined to specific energies that we call energy levels. Okay? Now, instead of having the circle, where we think a particular electron is going to be located is an orbital. Every electron could be in a different orbital, and an orbital is an area around the nucleus where electrons of specific energies are most likely to be found. So an orbital, an area around the nucleus where electrons of specific energies are most likely to be found. It is three-dimensional, so we got to take our 2D stuff that we're putting on paper and think in 3 dimensions. It's nothing physical. It's just what equations tell us that, hey, the electron, where it's going to be, it's probably going to be in this area, but it's not like there's actually a, balloon around that area that the electron is inside of. How do we get these orbitals? How do we know where the electrons are going to be? It's going to come from math, and it's math that we don't ever hit on, even in most undergraduate programs. You don't hit on a lot of the math involved with these orbitals. But what I'll try to show you is sometimes the end result. So we get this equation, we get this math stuff, we plug in some information, and what it's going to do is it's going to spit out what's called an electron density plot. In this electron density plot, every dot represents where the electron could be. I don't know if it's there, but given our mathematics, our probability models, we think the electron could be in that spot. So maybe there's a dot right here. The electron could be there, which, by the way, the origin is the nucleus. But it's not just going to give me one. It's going to give me several different possible locations for that electron of that particular energy. So here, maybe there's one here. Maybe there's one here, here, here. Again, each point is not the electron itself. Each point is where that is a probable location of an electron. So maybe we have something like this. So when scientists looked at this plot, and again, we have to extrapolate out to 3 dimensions, they were like, well, this kind of looks like a shape, right? The way that the points are all arranged, it kind of looks like a circle. And they're like, cool, well, we're going to call that little circle bubble area, we're going to call that an orbital. There's no actual ring around it. It's just a little cloud thing that they're like, hey, in that space, that's where we think that electron's going to be. Hey, this is one of our orbitals. But not all of the density plots have the same look. I could have done another electron density plot, and it might have looked like this. Where there was really no electrons directly around the nucleus, but they all seem to be kind of clumped on either side of the nucleus. That would be an electron density plot for a different electron of a different energy. And so scientists were like, oh, well, that's a different orbital type, right? Here's one orbital, and then there's this one that maybe we can say, oh, the shape looks something like this. Right? We often describe that shape as a dumbbell, because if we think of a dumbbell that's got the skinny handle in the middle that you hold on to, but then the fatter weights on the sides, the fatter weights, that's where the electrons could be, but they weren't really in there on the handle of the dumbbell. I sometimes think of it as two balloons tied together, right? Where you don't really have electrons in the middle where they're tied together, but they'll be on the sides. So I'm not going to draw any other electron density plots, but we come up with 4 different orbital types based on their shapes. So there are 4 different types of orbitals, and they have 4 different shapes. They were named S, P, D, and F. I don't know specifically where those letters came from. I think it relates to some mathematical equation. But we have S, P, D, and F, and they each have their own shape. The S was the first one that I drew up here. The S is described as spherical. Because you have to think in 3 dimensions. It's not just a circle, it's a sphere, it's a bubble. And so if we say, oh, that electron, is in an S orbital, that means it's somewhere inside of the sphere, and I don't know where. But inside of that area. And hey, guess what? I actually could have up to 2 electrons in that area. There could be 2 electrons with the same energy that could both be in that sphere. I don't know where in the sphere. And again, remember, the sphere is not a physical thing. It's just a space around the atom where they could be. All right, your p orbitals. Those are the ones described as dumbbells. And that's what we drew here. That would be a dumbbell. I'm going to show you computer pictures of these that are nicer in just a minute. Okay. And so, even though the P dumbbell looks bigger than the S sphere, guess what? There's still only 2 electrons with the same energy that could be somewhere in that dumbbell. And that doesn't mean I have to have one on the right and one on the left. I could sometimes have both of them on the right or both of them on the left. I don't know. I just know that they're likely to be somewhere in that dumbbell shape. Remember, that's probability model here. Heisenberg, we can't really know exactly where they are and where they're going, but we got pretty high degree of probability that they'll be somewhere in those areas. Right, as we move into D, it gets more complicated. If you were asked, a D orbital is often described as a cloverleaf, and a cloverleaf has how many leaves on it? 4. So I'm not going to make the density plot, but it could be like a 4-leaf clover. Like 4 balloons tied together. Unfortunately, there is one other D orbital that's a different shape. Nobody's going to ask you about this, but I want to put it in our notes. Dumbbell with a donut. It's a dumbbell, but it's got like a donut ring around the center. Aiden, you got a mask? Thank you. All right, and even though that's got 4 balloons, guess what? Only 2 electrons of equal energy can be in that cloverleaf. All right, and lastly, F. Guys, F is so complicated, there is no shape that we can use to describe it. There is no verbal shape to describe F orbitals, but I'll show them to you in just a second. And an F orbital can only have 2 electrons. Oh, we see the pattern there. It doesn't matter the shape. Doesn't matter how big or small we think it is. An orbital can only contain 2 equal energy electrons. Done. All right, so let's take a look at some pictures here. So here is a breakdown of all of the 4 types. At the top, we've got the S. There's our sphere. Here, this is a dumbbell. They're using the yellow and the orange for the 2 different sides of the dumbbell. Here, this would be a clover leaf. You've got 2 pink and 2 blue for the clover leaf. And also, if you're curious, there's that dumbbell with the donut. The 2 blues are the dumbbell, and then the purple is the ring for the donut. And then this would be an F. I would describe an F as 8 balloons tied together. So I really do like the balloon. Like an S is just 1 balloon, a P is 2 balloons, a D is 4, and an F is 8. But no matter how many balloons were tied together, only 2 electrons could be here, only 2 electrons here, only 2 electrons, only 2 electrons. No, question?
Yeah, could there be multiple orbitals with the same amount of energy?
We're going to get there. We are building, so we're just starting with the orbital and the different orbital types. All right, so now we know that there are different energy levels. But one thing that the Bohr model was not good at, that the quantum mechanical is going to do a better job, is the energy levels can be divided into sublevels. The energy levels can be divided into sublevels. When we divide our energy levels into sublevels, the sublevels actually have slightly different energies, but they're close enough that we still group them together on the same energy level. So to jump from a second to a third energy level would be a significant jump in energy, but the difference between the electrons and the sublevels, that's only going to be a small difference in energy. Another general rule of thumb, when you're closer to the nucleus on your first energy level, there's not a lot of room to have a whole bunch of sublevels. It's not until you get further away from the nucleus that you can have more sublevels. And that means, if you didn't catch that implication, guys, not every energy level has the same number of sublevels. It's not like every energy level gets split into 2 or 3. It's going to vary depending on where you're at. So for example, guys, the first energy level, guys, you don't split it. It is 1 sublevel, like that is the entire energy level. Come on, try this. The first energy level is just the 1 sublevel, and that's it. But the second energy level has 2 sublevels. So electrons could either be in the first sublevel or the second sublevel on the second energy level. The third energy level has 3 different sublevels. And then the fourth energy level has 4 different sublevels, and that's where we're stopping with our chart, even though you can have more energy levels in an atom. All right, so we name our sublevels. The sublevel names have 2 important pieces of information in them. The first one, it actually tells you what energy level you're on. So that's nice, just by the sublevel name. But the second thing it'll tell you is what type of orbitals are there. Because the sublevels are differentiated by, do they have spheres or dumbbells or clover leaves or 8 balloon crazy things. So here we go. That first energy level, the sublevel is called 1s. The 1 tells me we're on the first energy level. The s tells me I have a sphere. And then that is the entire first energy level. There's nothing else that you can have on the first energy level. Only 2 electrons will go there, and then the first energy level is full. Your second energy level has a 2s and a 2p sublevel. So first, the 2s tell me the energy level I'm at, and then I've got spheres, right, for the 2s, and I got a dumbbell for the 2p. Mrs. Tate, what is the difference between the 1s and the 2s? That's going to come down to how big the sphere is. So as your s number, the coefficient gets larger, a 1s is the smallest, a 2s would be bigger, a 3s would be a bigger sphere, a 4s would be an even bigger sphere, right? 6s, giant sphere. That's what we're changing is the size of the sphere, but they're all still spheres. And these 2 guys, they're not the exact same energy, but they're close. They're definitely a lot closer than they are to the 1s electrons. So that's how we know that they exist, is because they have different energy electrons. But we still group them together on the second energy level because of the fact that they're not really far apart. They're still pretty close, but not identical. Okay, so move into the third energy level. We have a 3s, a 3p, and a 3d sublevel. 3s, 3p, 3d. So again, the 3s is just a bigger sphere. Likewise, the 3p is just a bigger dumbbell than the 2p, but they're still dumbbells. And then now we have 3d, the cloverleaf. And so finally on the fourth energy level, 4s, 4p, 4d, and 4f. So from this chart, it is important to note that not every single type of orbital exists on every energy level. So for example, guys, there's no F on the first energy level. There's no such thing as a 1F sublevel. 1F doesn't exist. 2F doesn't exist. The first time you can have any F orbitals is going to be on the fourth energy level. And so I've seen those questions like, hey, what energy level is the first time you can have D or orbitals? That's going to be the third energy level, because 3D, 3 is the first time, third energy level. You don't have a 2D, you don't have a 1D. Those are not possible. They don't exist. So you got to have higher energy electrons to get up to the D and the F orbital types. All right, so we have orbitals, different types. And then now we know that energy levels can be split into sublevels based on the type of orbitals that are there. So, last big thing, each of these sublevels is not restricted to only having one dumbbell or one clover leaf or one 8 balloon thing. We can actually put multiple of those things together within a sublevel. Hey guys, I'm seeing a decent amount of phone action going on right now, which should not be happening while I'm lecturing. All right, so in this first column, we're talking about the orbital type or the sublevel. So when it says S here, this could be the 1s, 2s, 3s, 4s. I'm not specifying. Or here, this could be 2p, 3p, 4p. So any sublevel that has a p in it. And what we want to know is how many orbitals can actually be in that sublevel. Okay, so let's start off with the sphere. Guys, a sphere is a sphere, and you can't have more than one sphere in the same place without it just being right on top of the other sphere if you're at the same sublevel. So like a 1s sphere, I can't have two of those because they would just be right on top of each other. Yeah, it doesn't happen. The orbitals have to be in different places in space, and you can't do that with spheres. All right, so if all I have is one sphere, how many electrons can we put in that sphere? 2. There could be 2. All right, but now going up to the other ones, we're going to have some options. So when we think about a dumbbell, depending on how I think about that dumbbell, my dumbbell could maybe be going like along the x-axis if we're thinking of a coordinate system, kind of like I drew in the very first part. But I could also have a dumbbell going on the y-axis, up and down, and I could have the dumbbell going on the z-axis, forward and back, off of the page. That means I could combine 3 different dumbbells together, and that would make up what we call a P sublevel. So it's important that you guys are getting the vocabulary. An orbital is the dumbbell. 1 orbital, 1 dumbbell. But if I take 3 dumbbells and put them together in space, that makes a sublevel. So the P orbital is just a dumbbell. A P sublevel is 3 dumbbells. A sublevel can have more than 1 orbital in it. So let's look at a picture. Here, this is a P orbital. This is a P orbital. Notice they're different in space. This was on the X, this was on the Y, although that doesn't look like the Y, but that's okay. And then here, this one's on the Z. So those are 3 different dumbbells I color-coded for you. 3 different orbitals. But I put them all together This is a P sublevel. So you see how now they're all stuck together? That's the sublevel. So this could be 2P, 3P, 4P, and again, the difference between 2P, 3P, and 4P would just be how big the dumbbells are getting. So orbital, 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 but sublevel when you put those three orbitals together. So let's think about the electrons. How many electrons could go in a dumbbell? 2. So I can put 2 electrons here. I can put 2 electrons here, and I can put 2 electrons there. So then total, how many can go in this whole thing? 6. Now that doesn't mean I will have to have 6, but I could have 6. So anywhere between 1 and 6 electrons could go in the sublevel. So that's what we're going to get here, 6. Okay, for the D, remember the D is the clover leaf. For the clover leaf, you could have up to 5 of them. It's actually 4 clover leaves and then the dumbbell with the donut. That's why I say if you were asked for the shape, clover leaf is the shape because 4 of the 5 have to be clover leaves. Let's take a look at that one. Here's an image showing how all of the D orbitals would come together. So here's clover leaf number 1, clover leaf number 2, clover leaf number 3, clover leaf number 4. That's 4 orbitals right there. And notice they just keep turning the clover leaf in different XYZ plane orientation. And then here, there's your dumbbell with your donut. There's your 5th orbital. And all together now, that makes a D sublevel. Right? So that's the sublevel. Sublevels can have more than 1 orbital. An orbital, though, is just one of the clover leaves or one of the dumbbells, right? So let's think about electrons here. How many electrons can go in a clover leaf? 2. So 2 here, 2 here, 2 here, 2 here, and 2 there. So total, how many can I have? 10, right? 2, 4, 6, 8, 10. So 10 electrons in that one.
So it's not more electrons too?
Exactly, because each orbital can have 2 electrons. So you just double that number, that's how many electrons. All right, and so following the pattern, 1, 3, 5, 7. All right, you can have 7 of those crazy F8 balloon things. And if I have 7 orbitals, how many electrons would that be? 14. So I don't have them all superimposed on each other, but going back to this original picture here, guys, that's why they had more than 1. Here was your 1 sphere. There were your 3 dumbbells. They just didn't put them together. Here were your 5, your 4 clover leaf and a dumbbell with a donut. And then so these are your 7. They just keep taking and turning this 8 balloon thing on different XYZ planes. And then there's a dumbbell with the double donut in there. But there's your 7 that all together, all 7 of those make up a sublevel.
Do the sublevels get further away from the nucleus?
Yes, they do. So like a 4F compared to a 5F, the 5F is further away from the nucleus because it's bigger. Right, they're further from the nucleus. That is still true. Okay. So, guys, that's the basics of quantum mechanical. To try to help you remember this, what I'm going to do now is I'm going to make an analogy. So this doesn't have to be giant. I'm not writing a ton of stuff in this. But what we're trying to do is we're trying to relate this to having tickets to a show. Welcome to Adams Stadium. We have an excellent show in store for you tonight. First thing you're going to need to do is you're now going to need to locate your seat within Adams Stadium. So, in our stadium, we do have the stage down here at the bottom, kind of little amphitheater-like setup here. And if I had a ticket to a show at Adams Stadium, what is the very first thing that I'm going to need to look for on my ticket to figure out where to go?
Section.
Probably even before that.
Gate.
After gate.
Parking lot.
No, after the gate, but before the section.
Seat.
Oh, can't go to my seat yet.
Row.
What?
Row.
How would I, if I don't need to know where my section is yet, then why would I need to know where my row is? I think you guys are combining something with the section that we're missing that we're also going to have to know. Like what happens if I walk in by the parking lot, but I have nosebleed seats?
Oh, the tunnel. The entrance.
Yeah, why would I need a staircase? Because I need to know what level I'm on, guys. I gotta know what level.
You gotta know what section you're gonna know what level you are.
No? I gotta know if I gotta go upstairs or downstairs first, right? The section's gonna tell me if I gotta go right or left when I'm on my level.
Okay, I got it.
Right? I gotta know if I have to go upstairs or downstairs, depending on where I come in. Alright, so here we go. Adams Stadium. Adams Stadium has 4 levels. So on my ticket somewhere, I gotta figure out which level I'm at to figure out if I gotta go upstairs or downstairs. Alright, so now I'm on my level. What do I need to know next? The section. Alright, so now I start looking at the sections. So you see here, this is split up into our sections. Here, this is our 1S section. Here, this is our 2S section and 2P section. Then we have our 3S section, our 3P section, and then our 3D section. And then I think you can guess 4S section, 4P, 4D, and 4F section. And so, what you guys might have missed before, isn't it oftentimes that the section also tells us what level to go to? Like if I was in section 211, I know, oh, I'm on the second level because 211, the 2 tells me the level. Or if I have seats in 303, I know I'm going to the 3rd level, right? So same thing happened here, that my section probably told me what level to go to as well. All right, so now I'm at my section. What's the next thing I'm going to need to know? The row. Now I got to know the row. Am I going down to A? Am I going down to double C, whatever it is? All right. So we're not going to write down the names of the rows here, but we are going to write down that there is only one row in the 1S section, so that's nice. There's only one row in the 2S section, but this is a weird stadium. There's 3 rows in the 2P section. And then we've got 1 row in the 3S section, 3 rows in the 3P section, and 5 rows in the 3D section. And then still have 1 row in the 4S. We've got 3 rows in the 4P, 5 rows in the 4D, and 7 rows in the 4F. All right, so now I'm at my row. What's the last piece of information I need? The seat. So what we're going to add here is that all rows have 2 seats. So my ticket just better tell me, hey, which of the 2 seats am I in? The first one or the second one? So if we think of our atom like a stadium, every electron in an atom has to have its own ticket. And that ticket needs to convey all of that information, the level to go to, the section to go to, the row, and the seat. So I don't want to have wasted our time entirely doing this. So I want to wrap up by making sure we are very clear about what things in our stadium are what parts of our atom. Let's make the connections. So let's start off with, what do you think the stage represents in the atom? It's the nucleus. The stage is the nucleus. Right? That's where the electrons go to first. They want to get closer to that. Nucleus. Okay. Our levels in our stadium. What do you think that relates to in the atom? The levels in the stadium are the energy levels. It's the same word, guys. They even have levels. Just put energy in front. So energy levels. All right, the sections. What do you think the sections are? Those are the sublevels. All right, what about the rows? Those are the orbitals, the different orbitals. So if I really was talking about my electrons, this would have to tell me, like for the P, if it was the X, P, the Y, or the Z, right? X, Y, Z, and the other ones were all the different orientations, right? Was it the flat one? Was it the one standing up? They have different ways to label that. All right, and then lastly, what do you think the seats are, or the people that will go in the seats? Those are the electrons. So with this understanding of how the electrons could be structured between energy levels, sublevels, orbitals, and then the actual electrons then. Now our job is to actually describe this for any atom on the periodic table. Right? So there are three main rules that we follow to decide how we're going to sell tickets. Right? We've got all these electrons. We've got this whole stadium where the electrons could go. But there are going to be rules about who we sell to first, which tickets get sold first, second, third, right, in our stadium. So, starting off with Pauli's exclusion principle. And I'm going to go back to our stadium analogy to introduce this one. And this is the idea that you can't have electrons with the same ticket. Like, you can't sell an identical ticket to two different electrons that are the same section, same sublevel, right? Same row, same seat. Everybody's got to have their own unique ticket. That's the idea with Pauli's exclusion principle. We say that no two electrons can have the same electron configuration. And again, the same electron configuration would be like the same ticket to the stadium. This usually isn't a problem because we've got a really good system with our stadium. We've got our sub-level names, right? We can even name our rows with the X, Y, Z. Where it usually comes down to are the seats in the same row. Like, how do we differentiate between the two electrons that both go into the same sphere? Or the two electrons that both go into the same dumbbell? We need to have a way to differentiate between them. So as it turns out, electrons spin. That's the thing that they do. They spin, right? So part of Pauli's exclusion principle that we'll see when we start drawing orbital diagrams is that we say that electrons in the same orbital, in our stadium, that would mean they're in the same row. We say that they have opposite spin. So on my ticket, it might say, hey, like you're in the clockwise seat, and then the other one you're in the counterclockwise seat. Like those would be the names of the two seats, clockwise and counterclockwise. So when we do orbital diagrams, we're going to be using arrows, and we'll have an arrow pointing up and down for meaning that they're spinning different directions. They sometimes describe upspin and downspin. All right, so that's an important one, but one that doesn't usually become a sticking point. Aufbau is the big one. Aufbau is a German word, and we've already mentioned this one. Guys, you can't start at the top of the stadium. The electrons are not going to those highest energy seats first. They are going to fill closest to the nucleus because those are lower energy. They want that ground state, right? Electrons going to the lowest energies possible, and that's Aufbau. Electrons must fill lower energy sublevels. Before they can fill higher ones. And electrons must fill lower energy. And notice it does go down to sublevels. It's not even just going to be based on the energy level. We're actually going to break it down into like 2s and 2p. Well, who comes first? 2s is going to be lower energy than 2p. Even though they're similar, it's still lower. With that, I'm going to scroll back up for a second. There's a lot of students who would be like, oh, well, we're just going to go in order here. 1s, 2s, 2p, 3s, 3p, 3d, right? And it does mostly follow that, but not perfectly. There are going to be some flip-flops. Things that are going to go out of order. A specific one, 3D and 4s go out of order. 4s actually fills before 3D because those electrons are lower energy. Not by a ton, but they're lower energy. Thankfully, we don't have to memorize those quirky things. We're going to be able to use a periodic table, and the periodic table actually put them in the right order for us with just a couple of tricks. So yay! Just know it goes low energy to high energy, and then we'll use the periodic table to figure out what that order should be. All right, last thing, Hund's rule. Hund's rule is for those like dumbbell things. I'm going to draw the picture and erase it. So if I've got my 3 dumbbells, go away. Come on. So dumbbell, dumbbell, and then dumbbell. If this makes up a P sublevel, let's say this is a 2P. These are all equal energy electrons. There's no difference in energy between an electron here and an electron there. So the idea is, if I have to put electrons in these orbitals, like how do I know which one to put first? Where do I put the second one? Where do I have up to 6 I could put in here. How do I know where to put them? And that's what Hund's rule is going to help us out with, because Aufbau doesn't help here. These are all the same energy. If they're the same energy, then Aufbau doesn't help me. Aufbau only says lower energy first, higher energy next. So here we go. Let's write down what Hon says. Hon says each equal energy orbital at a sublevel. So that would be all those dumbbells at the same sublevel. They must have 1 electron before a second can be added. Each equal energy orbital at a sublevel must have 1 electron before a second one can be added. I like to think of this as, guys, like if you're on an airplane and everybody's traveling by themselves, no families, no couples, everybody's by themselves. Like, are you really going to double up in the same row with somebody if there's open seats available? Like, no, you're not going to double up unless you have to. And that's what's happening with Hund's rule. When I have those 3 dumbbells and they're all the same energy, these negative electrons are going to be like, why am I going to pair up if I have other equal energy places to go? Like, it's like the same level of ticket on the plane. I can go to these other open ones and get far away. So that means I'm going to put 1 electron here, 1 here, 1 here. And then if I still have more electrons in my atom, then I'll circle back and put the next one here, but only because Aufbau tells me I have to fill all of these energies before I go to the next higher energy one. So eventually I will have to fill them, but I won't double them up until I absolutely have to. So that's Hund's rule. So we're going to stop with that today. I know there's a little more up there, but early release, didn't have time to get to it. Tomorrow we really jump into those configurations though. Electron configurations and orbital diagrams.